The next case study that I would like to talk about is called IceBat. So that stands for Innovative Carbon Electrodes for Batteries. It has nothing to do with ice and batteries. And this is a project that's recently concluded with Johnson Matthey and Thomas Swan. This is an Innovate UK funded project. And within this, we were looking at a couple of different areas. So that was looking at incorporating innovative carbons. So in this case, that was graphene nanoplatelets and carbon nanotubes. And also looking at alternative solvents and binder systems. And that's what I'm going to talk about in the next couple of slides. So for those less familiar with batteries, when you're looking to make a battery cathode slurry, a typical formulation would consist of your active, a binder, a conductive additive, and a solvent. You combine those together to form a slurry, which you would then coat onto a current collector, which would be a copper or aluminium foil, depending on whether it was an anode or cathode. And then you would dry that, calendar it, and ultimately put it together into a complete battery for electrochemical testing. So a typical slurry formulation for the cathode would have PVDF as the binder and NMP as the solvent. Now these are used widely primarily because they're very good at what they do. However, they do have a number of drawbacks. So for instance, NMP is quite a high boiling point, so it takes a lot of energy to dry the coated foils. It also has concerns around safety and regulatory aspects. PVP, on the other hand, isn't ideal for recycling batteries at the end of life. So we were interested in greener, more sustainable alternatives, ideally with lower boiling points, and also potentially looking at alternative binders that would be soluble in these greener solvents of interest. So to do this, we use principal component analysis again. But in this instance, we weren't looking for a diverse spread of solvents. We were looking at solvents that would show very similar properties in component space to NMP. So as you can see from the component map here, this allowed us to narrow in on the area around NMP for our experimental campaign and actually pick solvents that would have a reasonable chance of being successful. So we screened a wide range of different solvents and individually and in combination, and also a wide range of different binder materials. So this project was around 400 samples. And we were screening for both dissolution, but also for rheology. So it wasn't sufficient for the binder to dissolve. We needed a polymer solution that would actually have a fighting chance of actually being able to be coated. So something that wasn't going to gel, for instance. So I'm pleased to say that we managed to find a number of promising candidates. What was also very nice is the results that we expected based on the PCA were actually confirmed experimentally. And then based on this, we were able to take the best candidates through to screening within full cathode slurry formulations. And we're seeing some really promising results coming out of that with our partners.
Excellent. Thank you, Lynn, so much for that great presentation, and congratulations on your shared accomplishments. It's super insightful to see how the team at CPI are using flexible Chemspeed automation platforms to accelerate their product development across so many different industries. We truly look forward to continuing to support you in this endeavor. And with that, we'll now move to a quick Q&A session. So if we're not able to get to your question, we can follow up with you after the webinar via email. So first question, please. Okay. Thanks for your excellent presentation, Dr. Donlon. Are there any case studies that you can share with the audience where your automated systems have been applied?
So obviously I gave a few case studies within the presentation. We've obviously completed a number of other projects for clients that I'm not really in a position to talk about. A lot of these projects can generate a wealth of data. So very often we're looking at making several hundred formulations across a few weeks. So within these projects, we're able to generate a large amount of data and get our customers to the answers that they're looking for more quickly. So we've worked on projects across a wide range of different sectors, and hopefully the talk will have given you a flavour for a few of those, certainly not all of them.
Great. Next question. So you've talked about formulation processes. Are you able to carry out material synthesis as well?
So that very much depends on the synthesis. Generally, our platforms have been geared more towards formulation development rather than synthesis and materials discovery. So for simple synthetic procedures, we probably could do that with the capability that we have, either just reactions in vials or within formulation vessels. For more in-depth chemistry requiring specific conditions, so for instance to work under pressure, then we would need dedicated synthetic reactors. So we would be able to retrofit those onto our systems. To date, because we've been more formulation rather than synthetically focused, we found that we've not really needed that capability specifically, but we do have the ability, with the flexibility of the systems we have, to retrofit that should the need arise in the future.
Very good. Next question. What are the most critical parameters for good battery materials, and how are they measured?
Okay, so that very much depends on what's meant by battery materials. So if you're talking about the actives, then that very much depends on what you're planning to use them for specifically in the end application. So I'll answer this in terms of slurries instead. So the most critical parameter for us is rheology. So we need that material to flow in order to coat, but have sufficiently good recovery to not then spread once coated onto the foil. So the first thing that we screen for is rheology. Particle size is also important. So you want to make sure that you don't have agglomerates within the slurry. Beyond that, on the coated foils, then we tend to be looking for things like adhesion of the slurry to the foil, and then ultimately electrochemical testing. But generally, those measurements are more time consuming, so we want to down select the less than ideal formulations at an early stage and only take the best candidates through for screening, or for full characterization, should I say.
Excellent. And one last question looking at the time. So compared to manual work, what was time saving in the various projects that you talked about?
So for the Liebed polymer example, we're probably looking at a couple of days to make and test the samples on the robots versus probably at least a week, probably longer, to make those by hand. When we get into, for instance, the ice bat project, for 3 or 4 component systems, we did that, if I remember correctly, in about a fortnight for the make and test. That would have taken weeks, if not months, to do by hand. I would say typically we can be looking at hundreds of formulations within a few weeks for a lot of the campaigns that we do. But as with all automation campaigns, a lot of the work is in the early stage setup, so developing the workflows, setting those up and optimizing them, and then the throughput tends to become exponential from there.